In this lecture we deal with fixed points and linearization. So consider the system x dot is equal to f of xy, y dot is equal to g of xy, and we suppose that x star, y star is a fixed point. So f of x star, y star is equal to 0 and g's of x star, y star is equal to 0. So let u is equal to x minus x star and v is equal to y minus y star be small disturbances from the fixed point. Now we need to work out if the disturbances grow or decay. So we now derive differential equations for u and v. So let's first focus on the u equation. So u dot is equal to x dot, and that's as x star is a constant. This is equal to f of x star plus u and y star plus v, and this is by a simple substitution, and this expands to f of x star y star plus u times df dx plus v times df dy plus terms that are order u square, v square and uv, and this comes by employing a Taylor series expansion, and this is equal to u df dx plus v df dy plus terms which are order u square, v square, uv, as f of x star, y star is 0. Now note that df dx and df dy are to be evaluated at the fixed point x star, y star. So in a similar way, v dot is equal to u dg dx plus v dg dy plus terms which are order u square, v square and uv. Note that order u square, v square, uv denotes quadratic terms in u and v, and since u and v are small disturbances, the quadratic terms are in fact very small. So the disturbance uv evolves according to u dot v dot is equal to df dx, df dy, dg dx, dg dy times uv plus quadratic terms. So the matrix A is equal to df dx, df dy, dg dx, dg dy evaluated at x star, y star is called the Jacobian matrix at the fixed point x star, y star. So the non-linear system is x dot is equal to f of xy, y dot is equal to g of xy, where x star, y star is a fixed point, and the associated linearized system is u dot v dot is equal to df dx, df dy, dg dx, dg dy evaluated at x star, y star times uv. Now let's consider the impact of small nonlinear terms. So the question we have is the following: is it really safe to neglect the quadratic terms in the original nonlinear system? So another way to ask the question is the following: does the linearized system give a qualitatively correct picture of the phase portrait near the fixed point x star, y star? The short answer is yes, but we have to be very careful. So if the linearized system predicts a saddle, a node, or a spiral, then the fixed point really is a saddle, a node, or a spiral for the original nonlinear system. The borderline cases, i.e. centers, degenerate nodes, stars, or non-isolated fixed points, have to be treated much more carefully. So let's consider an example. Find all the fixed points of the system x dot is equal to minus x plus x cube and y dot is equal to minus 2y, and use the technique of linearization to classify them. Additionally, check the conclusions by deriving the phase portrait for the full nonlinear system. We know that the fixed points occur where x dot and y dot are equal to 0, and hence x is equal to 0 or x is equal to plus minus 1 and y is equal to 0 are the fixed points. So we have three fixed points: 0, 0, 1, 0, and minus 1, 0. Now the Jacobian matrix at a general point xy is A is equal to dx dot dx, dx dot dy, dy dot dx, and dy dot dy is equal to minus 1 plus 3x squared, 0, 0, and 2. Now we evaluate A at the fixed points. At 0, 0, A is equal to minus 1, 0, 0, minus 2. And so 0, 0 is a stable node. At plus minus 1, 0, A is equal to 2, 0, 0, minus 2. And so 1, 0 and minus 1, 0 are both saddle points. As we have stable nodes and saddle points, the fixed points for the nonlinear system are in fact predicted correctly. Now let's check the conclusions by deriving the phase portrait for the original nonlinear system. Note that the x and y equations are uncoupled, so we have two independent first order systems at right angles to each other. In the y direction, all the trajectories decay exponentially to y is equal to 0. In the x direction, the trajectories are attracted to x is equal to 0 and repelled from x is equal to plus minus 1. The vertical lines x is equal to 0 and x is equal to plus minus 1 are invariant because x dot is equal to 0 on them. So any trajectory that starts on these lines will stay on them forever. Similarly, y is equal to 0 is an invariant horizontal line. Finally, note that the phase portrait would be symmetric in both the x and the y axes. As the equations are invariant under the transformations x to minus x and y to minus y. So we now put this together to arrive at the phase portrait. So that's one fixed point. That's the second fixed point. And that's the third fixed point. And so we go ahead and fill out the rest of the phase portrait for this nonlinear system. So note that 0, 0 is a stable node and plus minus 1, 0 are saddles. And this is exactly as expected from the linearization. We now offer some comments on hyperbolic fixed points, topological equivalence, and structural stability. If the real part of lambda is not equal to 0 for both eigenvalues, then the fixed points are called hyperbolic. The stability of hyperbolic fixed points is unaffected by small nonlinear terms. Non-hyperbolic fixed points are the fragile ones. So here is a simple example of hyperbolicity. From our study of vector fields on the line, recall x dot is equal to f of x, and that the stability of a fixed point is accurately predicted by the linearization as long as f prime of x star is not equal to 0. Now this is the same as saying that the real part of lambda is not equal to 0. So the fixed point of an nth order system is hyperbolic if all the eigenvalues of the linearization lie off the imaginary axis, i.e. the real part of lambda I is not equal to 0 for I is equal to 1 to n. The Hartmann-Grobman theorem states the following. The local phase portrait near a hyperbolic fixed point is topologically equivalent to the phase portrait of the linearization. In particular, the stability type of the fixed point is captured by the linearization. Topologically equivalent essentially means that there is a homeomorphism, which is a continuous deformation with a continuous inverse that maps one local phase portrait onto the other, such that trajectories map onto trajectories and the sense of time, meaning the direction of the arrows, is actually preserved. Here is another way of thinking about it. Two phase portraits are topologically equivalent if one is simply a distorted version of the other. Hyperbolic fixed points also highlight the notion of structural stability. A phase portrait is structurally stable if its topology cannot be changed by an arbitrarily small perturbation to the vector field. For example, the phase portrait of a saddle point is structurally stable, but a small amount of damping can actually convert a center into a spiral.
Now in this lecture we dealt with a very important topic called linearization. So you can start with a two-dimensional flow of the form x dot is equal to f of xy and y dot is equal to g's of xy, where this nonlinear system has an equilibrium point denoted as x star, y star. So then what one can do is the following. We introduce small disturbances u and v around the equilibrium point. We introduce these into the original nonlinear system and we take a Taylor series expansion around the equilibrium. In the Taylor series expansion, we only retain the linear terms, the quadratic and all higher order terms are discarded. So the resulting equation would be linear, and so essentially we have a linearized equation associated with the original nonlinear system around the equilibrium x star, y star. So the fundamental question that you really want to know is the following. To what extent does the linearized version give a qualitatively correct picture of the phase portrait around the equilibrium? Yeah. So to some extent is how much can we trust anything that we get out of this linearized system? And the answer is that if the linearized version predicts a saddle, a node, or a spiral, then the fixed point really is a saddle, a node, or a spiral for the original nonlinear system. So in a sense, this technique of linearization can be very, very powerful to get qualitative aspects about the phase portrait of the original nonlinear system, and we can trust this as long as we have a saddle, a node, or a spiral.